First of all, I am happy to welcome the chief guest, Dr.T.Jagadesh, who has an excellent background on today's topic, the research challenges in the manufacturing of composite materials, who has done an excellent work in this area. I hope the people will be very much benefited because of his speech. I welcome everyone who has gathered in this meeting. Now I request Mr. Sivalingam to introduce the chief guest to the August gathering and let the guest lecture start. Thank you.
Thank you. Thank you, Anand sir. Thank you, sir. Good morning to all. Dr. T. Jagadesh currently serves as an assistant professor in Department of Production Engineering at NIT Trichy. He received his PhD degree in micro manufacturing from IIT Madras in 2016. He has been a postdoctoral fellow in manufacturing engineering from IIT Madras during the period of March to May 2016. He received his BE Mechanical Engineering from Institute of Road and Transport Technology, E-Road, and ME Manufacturing from Madras Institute of Technology, Corombet, Chennai in 2011. His research include micro manufacturing, metrology, precision machining, additive manufacturing, laser-based manufacturing, finite element simulation, molecular dynamic simulation, design of machine tool, composites, tribology, and cryogenic engines. Now, I request Dr. Jagadesh to speak to our students and faculty members. Jagadesh. Dr. Jagadesh.
Yes, Sivalingam. Thank you, Sivalingam. So, shall we start? I'll share the PPT and then we can start. Whether my PPT is visible?
Visible, Jagadesh.
Okay. Then shall we start?
Okay, started. Okay. Carry on.
So, good morning to all. Myself, Jagadesh. I am working as a faculty in the Department of Production Engineering from NIT Tiruchi. So, today I am going to discuss about research challenges in manufacturing of composite material. So, this is the outline of presentation. So, first I'll start with what is meant by manufacturing and what is meant by composites and how we can manufacture a composite by conventional technique and what are the challenges are there. And we'll discuss about how we can manufacture a composite by additive manufacturing. Then we'll discuss about macro and micro scale machining of composites. Then the summary of this is the outline of the presentation. Before going to this topic, I would like to discuss two terms. One is called snorkeling and second one is scuba diving. How many of them have come across this word? If the students are there, then if it is interactive, then it will be good.
Something connected with swimming.
Yes, very good. So both are related to swimming activities. You can see in this picture, there are two pictures are there. Can you identify which one is snorkeling and which one is scuba diving?
The top one is snorkeling and the bottom one is scuba diving.
Yes. Yes, correct. First one is a snorkeling, second one is a scuba diving. So both are related to swimming activities. For both the activities, we need mask, breathing tube, and other necessary equipments to be safe. So I am talking about these two things. So in snorkeling only you can see the surface of the water. Whereas when you go for a scuba diving, you can go deep inside a sea and then see what is there inside the depth. So I am telling these things whenever you do some project, whenever you do some research on any topic, we need to go in depth. It should not be at a surface level. So you have to find out the reason and you have to go in depth analysis. That is the point that I want to convey from this slide. Before going to composites, first we'll try to understand what is meant by manufacturing? In a simple layman words, can you define how one can define manufacturing? So it is the conversion of raw material into finished product. So either you take building an aircraft, let us take I'm building an aircraft or building an automobile or building any component, plastic component. So it's not a one-step process, building a missile, building a train or building a machine tool. So all are manufacturing or building a medical components. So all are the examples of manufacturing. It is not a one-step process. It has to undergo several manufacturing process. So starting from primary manufacturing process, then secondary manufacturing process, then assembly and testing, finally we'll make a product. So we'll take a typical example of aircraft and then we'll try to understand. Can you guess how many number of parts are there in aircraft? Approximately?
40.
Yes, 40. It's millions of parts are there. To take a Boeing 777, there are 6 million parts are there. So I'm talking about each and every small elements also. If you consider, there are millions of parts are there. So each part material is different, shape is different, size is different, and manufacturing process is different. It's not an easy. So building an aircraft is not an easy task. Only two companies are very famous in building an aircraft. One is Boeing and other one is an Airbus. Because you see the materials are different, shape is different, size is different, the manufacturing process is different, testing route is different. It's not an easy task. So building an aircraft. So we'll see in the next few coming slides how composites are widely used and which are the parts are used, how to manufacture it, what are the challenges are there. These are the things that we are going to discuss in this presentation. So the scope of manufacturing, the scope of composites not only in aircraft, so even automobiles also. If you take an automobile, you'll be having 15,000 parts are there. So now to reduce the weight, now they are looking to manufacturing. Suppose you want to increase this. So composites is the beauty in the composite is you can play in that. So whatever the required properties, suppose I want to improve the thermal properties, yes, we can build a composite. If I want to improve the mechanical property, if I want to improve the creep strength, improve the tensile strength. So all those things are possible with the help of a composites. So not only in automobile applications, suppose I am building a ship, building, what is this? Have you come across this one? It's a bullet train. So it will goes at the speed of 40 kilometers per hour. So how to build? The scope of manufacturing is enormous in these applications. So many have been come across this Titanic ship. So many might have been watched this movie, this Titanic ship failure. This happened because of failure in the selection of material. When the material has sudden transition has happened from FCC to BC structure, when it hits the iceberg, finally the catastrophic failure has happened. So why I am telling all those things? So whatever we are developing, finally we need to be safe. Whenever we are traveling in aircraft, whenever we are traveling in automobile, ship or train, we don't want any failure to happen. So as an engineer, as a manufacturing engineer, we need to make ensure the quality as well as the qualities play a very important role. Finally, we need to be safe. Just I've given only, so far we have discussed about what is meant by manufacturing and we have seen some applications scope in automobile and aerospace applications. Now we'll try to understand, now we understand what is meant by manufacturing. It is a conversion of raw material into finished product. Next, we'll try to understand what is meant by a composites. Everybody may be familiar in composites. So the composites will be having two constituents. One is matrix and another one is a reinforcement. And the property what you are getting in the composites is superior, it's better when compared with the individual components. So when you take composites, if you look into the history of composites, this composite is not a new. So if you look at this picture schematic diagram, you can see it has started earlier days. So these polymers, composites, ceramics. So over the years, there are a lot of development in reinforcement. There are development in matrix, and now they are trying to print the composites also, even metal as well as polymers. So we'll see all those things in next few coming slides. So how one can classify a composite? composites can be classified in 3 ways based upon the reinforcement matrix. Based on the matrix, suppose if you take matrix, there are different types of matrix one can be possible. Either it can be a metal or ceramic or polymer. So these are matrix. When you add as a reinforcement, then it will become a composites. So suppose take a metal matrix. Aluminum can be considered. Take on an example. Aluminum can be a metal, and you can add a reinforcement as silicon carbide or aluminum oxide. Then it will become a metal matrix composite. Whereas in case of ceramic matrix composite, the base will be the matrix will be the ceramics. Then you can add a reinforcement based upon your requirement. If you want to improve the toughness or improve the strength based upon the requirement, then you can add the reinforcement. Then the polymer matrix composite. So a base will be polymer, and then you can add a fiber as a reinforcement. One way of classification. The other way of classification is based upon the particle shape. You can see the particles can be a laminates. If it is a laminate, then we can consider as a laminate composite. If it is a fiber, then it can be a fiber composite. Either it can be a continuous or short fiber, or if it is a particle, then we can call it as a particle composite, flake composite, filled composite. So based upon the shape of the constituent, what you are choosing as a matrix in reinforcement, then we can classify in this way also. So in polymer composite, the base matrix, mostly it will be a polyester or epoxy, and then we'll add a reinforcement. So there are a lot of research work has been done in add as a reinforcement like a glass fiber and carbon fiber. And there are a lot of, so before going to develop a composite as an engineer, we need to understand the basics. To start from the scrap, how the structure has been, how the properties. So we all be familiar with the properties of the material mainly depends upon the structure. So like in metal, we'll be having a BCC, FCC, HCP structure. Similarly, in polymer also, suppose if you take a polymer matrix composite, you need to understand the structure. Suppose you take a polyester or epoxy resin or any other matrix. So as an engineer, straight away, one should not go for an experiment. You need to start from the basics. You need to start from the fundamental, how the strength has been improved. So let us take how we can define a polymers. When the monomers are combined together, then it becomes a polymer. Again, polymer will have a different classification. So like polypropylene, polyvinyl chloride, polystyrene, polytetrafluoroethylene. So these are all the examples for the strength. So how the structure, so we are seeing the different structures. So how one can say that which one will be having a more strength and which will be having a strength, which less strength. It depends upon the structure. Like how there in metals will have FCC, BCC. Similarly, here also we'll be having a structures. Suppose the linear and branched structure, these are all having a less strength. When the structure becomes more complex like cross-linked and network, then the strength will be getting improved. So this one has to understand before choosing the matrix. Then reinforcement. So reinforcement, you can see there are a lot of research is happening. So in polymer matrix composite, either they will add as a carbon fiber or glass fiber or Teflon fiber. Now they are adding more natural fibers also. There are a lot of scope in there, so a lot of work has been done. But one has to do, instead of going for experimentation in all the composites, it is highly expensive. So one can start with modeling and try to understand the physics of the process. Then you can go for an experiment. Then it will be more useful also when you are doing a research. So this understanding has to be more important. So you can add any natural fiber. So if you consider natural fiber alone, the strength will not be good. So one can do a natural fiber can be added along with the other fibers like carbon fiber and then this fiber. So the strength also will be good, and then you are using a natural fiber. So in that way, one can go. So once you add this reinforcement, either a natural fiber or a common fiber, carbon fiber or Teflon fiber. So what has to do is, so you have to find out the strength. So there are a lot of research. This is the first step one has to do. So what will be the strength of the fiber, and then you can see what is the strength of the matrix. And when you are adding a composite, depends upon what type of fiber and what type of the natural fiber is. So your strength belongs to that one. So this has to be very clear. What will be the yield strength of the material? What will be the ultimate strength, fracture strength? These are the properties one has to analyze after manufacturing a composites. So far we discussed about polymer matrix composites. So you'll be having a base polymer, and then you can add any reinforcement. So either you can add a natural or natural along with the carbon or other composite. So once you have made the composite, then you have to go for a testing and then find out what will be the strength when you are adding a natural fiber. So which will be, what will be the volume percentage, what will be the weight percentage if you add how much strength. So this experimentation always be an expensive. The challenge is one can develop in go for a modeling. So either you can go for a finite element model, or you can go for some analytical model and then try to understand the physics of the process. Then if you go for manufacturing, then it will be more useful. So the next one is a metal matrix composite. So what are the challenges are there? So far I'm talking about all in conventional. So in the latter we'll discuss about an additive, advanced manufacturing, additive manufacturing, and then the secondary. These are all the primary way of manufacturing process. Suppose you want to build a component with some holes or some complex shapes that you want to make. It's not an easy task by using a conventional manufacturing process. Suppose you want to manufacture a component with the holes has to be there. So it's not an easy task. So then you have to go for a secondary manufacturing process. Primary manufacturing alone, we cannot make these complex features as well as micro features. So for that, we need to go for a secondary manufacturing process as well. So next, we'll try to understand what is metal matrix composite. So in metal matrix composite, your matrix will be a metal, and then the reinforcement, we can add it as silicon carbide or aluminum oxide. So before going for metal matrix composite, first you will pick an element from the periodic tables. You all been these things you have been studied in school days about periodic table. So there are 118 elements are there. So before going to choose a matrix, one has to look into what will be the atomic number and mass number. We need to understand from the structure, from the atom level. We need to understand, because we are adding with the reinforcement, and then we need to see how these two materials are the interface is there. So all those things we need to understand. So the basic process in metal matrix composites is casting. Everybody will be very familiar in casting. So you'll create a mold cavity and you melt the material and you pour the liquid metal inside the mold and allow to solidify. Finally, we'll get the cast compound. So it's very clear in this process. But when you are adding a reinforcement like silicon carbide or aluminum oxide, so the problem here is it should be uniformly distributed in the matrix. So for that, a lot of research is going on, and then one can look into more simulation also. So because this experimentation is always a challenge and difficult. So before going for experimentation, you can do this casting simulation also. There are some softwares are available. You can actually create the matrix and then create the reinforcement, and then you can do the simulation also. So further on to improve their properties, then we can go for metal forming process. Once you have developed a composite, further I want to enhance the properties of the material, then one can go for a metal forming, where you can do a severe plastic deformation, then the properties will be getting improved. So you can see in this picture, so you can see initially you will be having a coarse grain structure, and after deforming the material, you can see the grain structure is getting refined. So we all been very familiar in Hall-Pitch equation. In Hall-Pitch equation, we know sigma y is equal to sigma naught plus a divided by root of d. So when the grain, that is when the grain size is getting reduced, then the strength will be getting improved. So this can be done. So in composite, after making the composite by casting process, you can go for further deforming a material, and then you can introduce a fine grain. So fine grain means the strength will be high. But this will be good only at a room temperature. This fine grain is good only at a room temperature. And when the temperature increases, then we need to choose a coarse grain. Normally in aircraft gas turbines, blades and all, normally it will be made of a single crystal material, because this fine grain will not be good for a high temperature. This is good only for a room temperature application. So the next question will come, whether all the materials, suppose you take a periodic table, whether all the materials can be castable. Can we cast all the elements here, whatever you are seeing the periodic table, whether all the materials can be castable? So if any yes, if any students are there, you can respond. Yes, all the materials we cannot cast. Why? The material is having a high melting point, then we cannot go for a casting process, because high melting point, suppose you take 2000 or 2500, 3000 degrees Celsius, like if you take a refractory metals like tungsten, molybdenum, vanadium, those materials we cannot cast. because there is no furnace available in the world to melt a material up to that temperature. Then it will be a difficult, it will be highly expensive. So then they will go for a powder metallurgy process. So where all will be familiar in powder metallurgy. But what are the challenges in powder metallurgy? The basic step is we need to produce a powder. So how to produce a powder? Again, there are different elements are there. If we go to periodic table, again, we cannot choose one process. So there are 118 elements are there. We cannot choose. There are n number of processes are there. So atomization, again in atomization, you have gas atomization, water atomization. Again, gas, there are different gases are there. And there are ball milling is there. So there are first step in powder metallurgy, you have to produce the powder. So producing the powder is always a challenge. It's not an easy task because in each technique, the powder quality will be different, size will be different, shape will be different, and then the cost will be different. So as an engineer, you need to understand this. Not only making a composite by powder metallurgy, you need to see which method will be suitable, because at the end, so what the company will be looking, they want to always improve their productivity, improve their quality, and they have to reduce the cost. These are the basic goals of any any manufacturing industry. So this is a very important process in powder metallurgy. First is selection of metal powder, and then what selection of metal powder production. So once you produce the powder, the next challenge is you need to design a die. Because when you are removing the compacted specimen, the specimen should not get break. So we need to have properly designed. Then we need to go for a sintering. Again, sintering, there are advancement has happened. So in early days, they used to do this conventional sintering, then micro sintering. Now they are going for a sparkless machine, so where you can improve the properties, and then you can. So basically, in sintering process, where the bonding will be happening between the particles. So there are a lot of scope in the powder metallurgy also. So far we have discussed about the conventional way of making components, which we are very familiar: the polymer matrix composite, metal matrix composite, and then ceramic matrix composites. So next, in few coming slides, I'll just show the application so that you will really appreciate the importance of composites in these applications. You can see normal the musical instruments or sports instruments. Easily you can manufacture with the help of a composite. You can see the bicycle and laminated fiberglass. And then in aircraft, if you take a Boeing 777, you can see it's all polymer composite they are using. Toughened graphite, graphite reinforced material, hybrid materials. So hybrid means you can mix with more number of fibers. So either you can add with a natural fiber, and then carbon fiber, Kevlar fiber, and then fiberglass. So the application is enormous, almost aircraft and automobile application. You can see in defense industry also we can use these composite materials. So you can see there are different fibers, and then based on it's all the components are not same. That is what I have told in the earlier also. The component, each component, the material will be different, shapes and size, and the processing route will be different. See, I'll just quickly go through because I have a lot of applications here. You can see in metal engine components also, you can entire thing you can make it by a composite material. And then you can see this the tailpipe. So the weight has come, and then the wind turbine blades, constructions, medical applications also. You can make the composite processes, and sports applications. You can see the cycles, and then the musical instruments. So all those things are made by composites. You can see the furnitures. So far we have discussed about conventional way of making a composite and then the application. So far I have discussed about what is meant by manufacturing, what is meant by composites, and how we can make by polymer matrix, metal matrix, and ceramic matrix composite, and then the application. So the next we'll move into additive manufacturing. So we are all familiar, I guess, in additive manufacturing. Also, it's again, it's not a new process. It's a layer by layer making process. So the beauty in that additive manufacturing process is here we can make complex features. Whereas in the case of conventional manufacturing, we need to prepare a mold. So making a complex feature in conventional manufacturing process is difficult. Either it is a polymer or metal matrix composite. Making a complex feature is difficult. Whereas in the case of additive manufacturing, the beauty here is we can make a complex feature also. So how the process has been done, it's like a 3D printing, making a component by layer making process. It's a layer by layer making process. Again, here we have 3 types of classification. One is stereolithography process, The second one is fused deposition modeling. Third one is selective laser synthesis. So here how they have classified this additive manufacturing into three types based upon the raw material use. Suppose if I am using a raw material as a liquid, then we can choose a stereolithography process. If the raw material is in the form of a solid, then it is a fused deposition model. Suppose if the raw material is in the form of a powder, then it's called a selective laser sintering. So using these techniques also, we can manufacture a composite. So we'll try to understand what is stereolithography was, what is mean by fused deposition and selective laser sintering. So in the basic step in all these processes, all these three processes, first we need to prepare a 3D computer aided design model. Suppose what is the shape that you are going to make. The first step is first we need to prepare a CAD model, 3D model. Then we need to convert the 3D model into STL format, that CAD data into STL format. This is the second step. The third step is we need to slice into number of layers. This is the challenge here. So how many number of layers? Suppose I'm going to, my objective is I want to manufacture a cylinder for aerospace application. Suppose you are going to, this can be made by a conventional manufacturing process also. Now I am talking about additive manufacturing. The additive manufacturing, first you will prepare this CAD drawing, then you convert that into STL file. Now I am going to choose the number of layers, slice layers, like S1, S2, S3 up to Sn. So how many number of layers that I can slice? Either I can go for 10 or 100 or 1000 or 10,000 or 1 lakh. Again, your property will be different. So there are a lot of challenges are there to deciding how many number of layers that you have to decide. Suppose if I want to print this material, I can print n number of layers. So how many number of layers will be better to get a better properties? How many number of layers one has to choose to get a better properties? That's always a challenge here. So the third step is you need to design the number of layers. So once you design, so this is the stereolithography process where the raw material is in the form of a liquid. You can see here it is a liquid. So now with the help of a laser, you focus at the place where you want to harden the material. Normally in a casting process, when the liquid is converted into solid, then we can call that as a solidification process. Whereas here also the raw material is in the form of a liquid. So when you focus this laser, so there is a process called here, the solidification, we used to call it as a curing. So when you focus your laser at a particular place where you are focusing, there the material will become hardened, and then you will get a layer 1, S1. Then with the help of this platform, you move this platform down. You can see when you move the platform down, then you will get the second layer S2. When you focus, then the second layer will be getting hardened. So how many layers that you have designed earlier? So based upon that, slowly you can cure one by one. So S1, S2, S3, S4, like that you can build a 3-dimensional component. So in the earlier cases, casting process, you will create a mold cavity, and then you will melt a material and pour the liquid metal inside the mold cavity and allow to solidify. So there, the entire bulk component will be produced. But whereas here, the component will be made by a layer by layer process. So what are the challenges, research challenges here? So here we need to find out how many number of layers one can choose. The next, when you go to an industry, they always look into productivity. How much time will be required to print one layer? So that depends upon, suppose I want to find out what will be the time required to build one layer. Let us take first layer that I am going to print. How much time it will be required? That depends upon the area. How much area that you are, if you mathematically, if you go, how much area that you are going to develop, area divided by V is the scanning speed of the laser beam, and then D is the diameter of the spot size, because you are going to focus a laser, what will be the diameter. So based upon this, one can find out what will be the time required to complete a single layer. So again, there will be a time delay, TD will come. So TD is nothing but time delay between a repushing of the table, because once one layer will get hardened, then again we need to move the platform down, the other layer will be getting hardened, again you need to move the platform down, third layer, fourth layer, fifth layer, like that you can develop a 3D model. But what are the challenges? Straight away you can go for an experimentation here also. When you develop a model, when you analytically, when you understand the process of physics, then it will be easy to go for an experimentation. Now this will be the time required to complete form a single layer. Suppose I want to find out what will be the total cycle time, because always they look into productivity. When you go for an industry, they will not look to manufacture a single component. They always look into how much time will be required to make 1,000 components or 10,000 components. So if you look into mathematical thought, what will be the total cycle time to complete a single layer? That depends upon, you can add all those layers. What will be the time? So then we'll get what will be the time required, build cycle time for completing the entire component. So this is a stereolithography process where the raw material is in the form of a liquid. You can see here, it is in the liquid. So here also, one can go for building a composite material. So by properly designing, you can go for building a composite. So the next process is a fused deposition modeling, where the raw material is in the form of a solid. You can see here, the raw material is in the form of a solid. So here we'll be having, here also we are going to print by a layer. So the methodology is same. These first 3 steps are same for all the process. First you need to build a 3D CAD model. Then we need to convert that into STL file. Then we need to decide how many number of layers that you are going to print. So you can see here the fused deposition modeling. So you'll be having you can see there are 2 spools are there. One can be used as a matrix, another can be used as a reinforcement fiber. So with the help of this, you can see the feedstock, the raw material is in the form of a solid. So this feedstock, normally it will be in the form of a wire. So these wires there will be a guide wire rolls will be there. With the help of that, we can feed this matrix and reinforcement inside the nozzle. The nozzle, there will be a heater. This heater will melt this solid and then it will deposit, you can see, layer by layer. So even you can print a multi-material also. One material may be A, other material can be B. So like that, it is possible to develop a composite materials. So this is one type of a technology where the raw material is in the form of a solid. Again, here also there are a lot of challenges are there. So what will be the layer thickness? What will be the orientation? Suppose you are building one layer A and then the other layer above that. So what will be the orientation? Whether the orientation is 0 degree or 90 degree or 45 degree, at what orientation that you are going to print. Based upon that, your properties will be varied. So there are a lot of research already has been done and still it is going on for printing a multi-material and then for composite materials. Next one is the selective laser sintering, where you can see the raw material is in the form of a powder. Suppose here also it is possible to develop a composite material with the help of this. So this technique is similar to powder metallurgy. In powder metallurgy, you will prepare a powder and then you will compact the powder with the help of a die and punch. Then you go for a sintering and then finally you will get a component. Whereas in the case of selective laser sintering, here also same, but you are going to develop by layer by layer. Suppose for high temperature materials, we can go for this kind of process. So here you can see these are all platforms where the bed will be there and then there will be a laser. So first they will pour the powder and then they will sinter it. They will level the powder. After pouring it, they will level the powder. They will sinter. So the first layer will be ready. Again, they will pour the powder with the help of a laser. They will scan and then they will sinter and then second layer. So like that, you can build composite material also with the help of this technology. So here, the beauty in the process is you can make a complex shapes. Suppose you want to make some complex aircraft turbine blade or some free-form surface if you want to make. When you want to make by a conventional, it is difficult because you have to prepare a mold cavity or prepare the die. Then you have to go for a machining process, bulk amount of material has to be removed. So all those challenges will be there in conventional. Whereas here, the beauty here is even the complex shapes can be printed by layer. But there are a lot of challenges are there. Not an easy process. So how much layer thickness one has to do? What will be the temperature, optimized temperature? And what will be, so there are so many challenges as the process parameter we need to optimize to get a better quality. Finally, the quality has to be good. That's what everybody will be looking. So far we have discussed about conventional way of making component, then additive manufacturing, advanced manufacturing process to develop a composite material. The next very important is, which I have told in the first slide, when you want to develop a product, it's not the raw material will be converted into finished product in one step. So it has to undergo primary manufacturing and secondary manufacturing. Normally the machining will be a secondary manufacturing process. So where what is the need of going for a machining? For all to get a good surface finish. This is the main objective of going for to get a good surface integrity. good surface finish. But machining is not an easy process. It is a complex manufacturing process where the tool and workpiece will be interacting at a higher speed. So where the material will be deforming elastically, and then plastic deformation. The energy consumed for plastic deformation becomes the heat energy. That heat has to dissipate. There are a lot of challenges are there. But when you are building a composite material, suppose you are building a metal matrix composite, a ceramic matrix composite by any technique, whether it is a conventional or additive manufacturing, you will not get the good surface integrity. Because all the functional surface, let us take all the functional surfaces, you always look into a good surface finish, which is not possible by a conventional or additive. We have to go for a machining process, at least a less amount of material has to be removed, and then we need to get a good surface finish. So that can be done only with the help of a machining process. But what are the challenges are there? So first, for building a machine tool itself is a challenge. So let us take a 3-axis CNC machine tool. There are 21 errors will be there. Because everybody will be thinking that when you have a machine tool, with the help of cutting tool, we can do a machining. It's not like that. If you go in deep, first we need to understand what are the errors are there in a machine tool. So suppose you have 3-axis machine tool, if you take, suppose the table will be moving in x-axis, you will be having a horizontal straightness error, vertical straightness error. We'll be thinking that when you see macroscopically, it look like the table will be moving perfectly fine. But when you, with the help of some laser, when you measure it, what are the errors in horizontal, in vertical, and straightness? There will be a 3. These are all the linear errors. If you consider one single axis, we'll be having 3 linear errors. And also it will act as a form error. So roll, pitch, and yaw. So if you closely observe, if you keep some angular sensor and then encode or something, and then if you measure, there will be an angular, there will be a form error also will be there. So in each axis, you'll be having a 6 error, like 3 linear error and 3 form error. So you'll be having a 3 axis. So 6 into 3, you'll be having 18 errors. In addition to that, there will be a squareness error between the 2 axes, the squareness error. So there will be a 3 square axis are there. So there will be a 3 squareness error. So totally there are 21 errors are possible. Why I'm talking all those things? Because once you develop a composite material, you will be going for a machining. So before going for a machining process, first you have to understand what are the errors are there, because these errors will affect your the component, workpiece component. So if the material, if the machine tool is having more form error, then you will not get the perfect. There will be the form error will be induced in your component. These things has to be, one has to understand before choosing a machine tool. First you have to understand how many errors are there, how we can minimize. There are a lot of research challenge going on, how we can minimize this error. We cannot make it 0, but we need to minimize as much as possible. So once you have a machine tool, now you understand about the difficulty in developing a machine tool, and then difficulty in manufacturing a composite. Now next you will go for a machining. When you go for a machining, you need to understand in depth how the material is removed. Suppose you developed a metal matrix composite. With the help of some cutting tool, you are doing a machining process, and then you will get the finished one. But as an engineer, you need to understand what actually happening during machining process. What is the mechanism of material removal? So now there people are talking about micro machining also. So what is the difference between macro machining and micro machining? Any guess? What is the difference between the macro machining and micro machining? So micro machining means you will be removing the component or generating a feature size in the terms of micron. Suppose you take any composite, polymer composite, you cannot create a feature which will be in terms of microns or nano level. So again, you have to go for a secondary manufacturing process. So what is the difference? Any guess? The difference between macro machining and micro machining? Any students there? So in macro machining, the material removal mechanism is, you can see here, if you look into, this is the workpiece material, workpiece, and this will be the cutting tool. So with the help of the cutting tool, so after developing a metal matrix composite, you will be looking for a good surface finish, so you'll be going for a machining. So when the tool is interacting with work material, in macro machining process, what you are seeing, this is a macro machining. In macro machining process, you can see the failure is happening along the grain boundary. Normally in grain boundary only will be weakened. So when the tool is interacting with the work material, the shearing will be happening along the grain boundary. So this is what will happen in macro machining. Whereas in case of micro machining, your feed and depth of cut, it will be in the range of microns, like 5 micrometer per revolution, like that. So suppose you take a grain size, suppose the grain size of the material is 10 micrometer, and then the depth of cut what you are giving is a 5 micrometer, the failure will be happening across the grain boundary. So it's similar like a stone. Suppose I'm giving a simple analogy. Suppose you take a more number of stones are there. I'll give an analogy. You take a stones, and then when you cut this stone, slice it, so it will slice along the grain boundary. So this is what will happen in the macro machining. The failure will be happening along the grain boundary. The failure will be happening along the grain boundary. Whereas in the case of micro machining, what you are seeing, this is a micro machining. Whereas in the case of micro machining, let us take a single stone, and when you want to slice it, is it easy to slice a single stone? So slicing a single stone is a simple analogy of micro machining, where you are sharing the material across the grain boundary. So it's not an easy task. So there are a lot of, because when you want to cut a stone, how much energy is needed to spend for that? So this one has to understand before going for machining of this metal matrix or any composite material. So here we cannot say in micro machining. So there will be one more issue will be there. We do not know that the material will be removed or not, because here the process parameter will be in terms of micron. Are you able to imagine the microns? It will be 1 micrometer or 2 micrometer feed or depth of that when you are giving. We don't know that the material will be removing or not. But the basic objective in machining is you need to remove the material, the chip has to form. But when you go for a micro machining, so when the tool edge radius is comparable to the process parameter, so all the time material will not be removed. There will be sometime burnishing or rubbing will happen. So because of that, the specific cutting energy, you see there will be specific cutting energy will be high for the low uncut chip thickness. When the tool edge radius is comparable to the uncut chip thickness, the specific cutting energy will be very high. So this is challenge. It's not an easy to micro machine any conventional material and composite material. So the other one more technology, with this I'll complete. So for such a high complex metal matrix composite or ceramic composite, if you want to process it and you want to generate a good surface finish, then you can go for a laser. So what you can do, you can use the laser to preheat the material and then you can remove. Because removing the material, conventional metal matrix composite or other material machining will be highly difficult, because tool wear will be there. Once tool wear, you will not get the proper surface integrity of the work material. So what there are a lot of research going on. One can improve the surface, because final objective is you need to get a good surface finish, even a conventional material or composite material. So what you can do, you can use a laser, focus just before removal of material. So you can see here, with the help of a laser, I'm focusing at the particular point. Then with the help of a cutting tool, we can remove. So what is the advantage or beauty in the process is, once you heat it, the material will get softened. Then you can easily remove the material with the help of a cutting tool. So that is the advantage of this laser assisted machining process. So this can be done at a macro level, but when it comes to micro level, again it's a challenge. Micro level means your component size will be very small in terms of 10 micrometer or 20 micrometer. So how will you focus on, how will you perform this micro machining is always a challenge. So you can see why the scientists and researchers are interested in this laser assisted machining, because you can see the total cost. So they will be not only interested in improving the quality, the cost, if you go through this laser assisted machining, you can see there is a drastic reduction. So that's why they are interested in this. So this can be not only used by a conventional material, even for composite material also you can use this technology for improving the surface integrity of the material. So, Sivalingam sir, how much time is there? Shall I conclude?
Yes, carry on, Jagadish.
Yes. Yes, there will be one more topic. I'll discuss this, and after that we can summarize the discussion. There will be one more topic called wettability. When you take a composite, so far we discussed about how we can manufacture a composite by conventional, and then how we can manufacture the composite by additive manufacturing technology. Then we have discussed about machining, because machining is important to improve the surface integrity of the material. So how we can do a machining in macro level, what are the challenges, and micro level, and then we can use this laser technology to improve the surface finishing of the material. So next topic I would like to discuss, with this I'll complete. So what is mean by wettability? It's very important because when you choose a matrix and the fiber as a reinforcement, so the interface has to be good. So how to check before randomly one cannot choose a matrix material and then fiber reinforcement and then one cannot go for a developing a composite. So the properties of fiber matrix reinforce interface, this interface play a very important role. So how to check the wettability? So how to find out the wettability of matrix and composite material? So there is one method. It's a well-known method. Many industry they used to follow this. So you can see here. Suppose I want to check the wettability between. Suppose I am going to print a multi-material. First, we need to understand what will be the wettability of material A. Suppose my objective is I am going to print a multi-material like composite material, material A, and then the second one is material B. I want to make the composite material like this. So first we need to understand in depth what will be the wettability between these two. So this test is called wettability test. I think maybe some of them may be familiar. So I'll explain how it can be done. First we need to choose one material, like material A need to choose. So this is material A. Then you take material B and melt the material B and once you melt, then it will become a solid. When you increase the temperature, then after reaching the recrystallization temperature or melting temperature, then it will become a liquid. And you pour one droplet of liquid over metal A. This is metal A and then this is metal B. So metal A I have taken as it is, and then metal B I have melted and I have poured a drop of liquid. Once you pour a drop of liquid and then you allow to solidify, then this also will become a solid. So material A I taken as it is, material B I melted, and once you melted it becomes a liquid, and pour one droplet of liquid metal over metal A and allow to solidify. So after solidification, then we need to check what will be the wettability angle. That's what they used to call as a wettability angle. You can see here, this is metal A, let us assume this is metal A, and what the droplet liquid, it becomes solidified, then this is a metal B. So after solidification, you need to check the wetting angle. So if the wetting angle is the angle between this surface and this surface, if you draw a tangent to this semicircle, then this is called the wettability angle. So if the wettability, there are two things we have studied in your undergraduates or in school days, something called acute angle, obtuse angle, or more technical, I can say it as a hydrophilic and hydrophobic. So if the angle is less than 90 degree, you can see it's having a good wettability. You can see here 0 degree. When there is a 0 degree, then there is no spreading. So less than 90 degree, we can call as a good wetting. When it is equal to 90 degree, then we can call as an incomplete wetting. If it is greater than 90 degree, the angle is greater than 90 degree, then we can call it as no wetting. So this you need to understand before going for making a multi-material or printing a multi-material or manufacturing a multi-material. Let us take an example, composite material. So it's very important just one has to perform and understand the wettability between these two materials. Then you have to go for a manufacturing a material, choosing any. So with this, I'll summarize. So we started with try to understand what is manufacturing, then what is mean by composite. Then we have seen the application of composite in aerospace, automobile, in ship industry, and medical industries. And then we have understand the applications. Then how we can manufacture a composite by a conventional, that we are very familiar, how to manufacture by polymer matrix, metal matrix, ceramic matrix, and how it can be done with the help of additive manufacturing. In additive manufacturing, we discussed about 3 techniques. One is stereolithography process, and then fusel deposition and selective laser sintering. Then we have discussed about the machining. So why we need to go for machining? To get a better surface integrity. So how the material has moved in macro level and micro level. And one has to look more into this modeling and simulation. So such a highly complex, because composite material is a complex process. So the properties are not isotropic, it is an anisotropic. So to understand those process, it's always advisable to start the work with the modeling and simulation. So understand the process physics, then we can go for manufacturing any material, whether it's a multi-material or composite. So with this, I'll complete this. If there is any doubt, then we can discuss now. Professor Sl.G.
Dr. Jagadesh?
Yes.
Okay. If you have
So
any
if there
doubts,
is,
ask me, dear students. If you have anything doubt, ask me.
Dr. Jagadesh.
yes, sir. Yes, please.
This is Suresh Pungaya. Your presentation are really awesome. So thank you very much for your unwavering attention through this presentation. So it's a nearly nice lecture and very useful content. Actually, I have two questions.
Yes, sir. Please.
May I know the difference between the compression molding and the layup methods of composite manufacturing?
Yes, sir. Compression molding is the conventional way of making a material. The conventional way of making this all we are fairly familiar with the one. But what is the need to go for additive manufacturing is, suppose you are changing the shape of a material, then again you have to prepare a new mold, new die we need to prepare. That will be highly expensive. Whereas in this case, only if you change the CAD model, then we can print even the complex picture also we can print with the help of an additive manufacturing. That is the beauty in additive manufacturing process.
Okay. And the second one is the future. So which biodegradable material will be replaced by plastics that is going out of production in the future?
That I do not know the exactly, sir. We have to look into literature. So there are a lot of research going on. So which material, because whatever the compound you are manufacturing, it should be a sustainable. So it should be a green manufacturing. That is what everybody will be looking. So that's why they are trying to introduce all the natural fibers in the composites.
Thank you, Jagdish. Thank you.
Okay, sir. Any other questions?
Any other?
Sir?
Yes, please.
I have one question, sir.
Your voice is very low. Can you speak louder?
Ramanish? Ramanish?
You have to unmute your mic and you have to speak, I guess. I think you are muted.
Yes, sir. Sir, can you hear
Yes.
me now?
Yes,
Yes,
please.
Sir, you before mentioned that before making the composite, you can simulate and see the and analyze it. So, what
Yes.
software can we use to do it, sir?
So yes, any FEA software you can use. There are several softwares like ANSYS, Abacus, and Deform software. Every software will be having some limitations, or you can write your own code also. That is also possible with the help of a MATLAB or any other software. You can write your own code and then you can develop according to your requirement. But that is not an easy task. But when you do that, you will be having a complete understanding about the process. Because when you do experimentally, it's an easy, anybody can do. Even if you give it to a lab assistant, he can develop a composite. So how it will be different from the, if you are engineer, if you are developing, you need to understand the process in a more better way. How you can understand? Only by developing a model or simulation. But for that, we need to start from the basics, start from the scratch level. So how, if you take a metal, start from atom, molecule, electron levels, you have to come. And similarly for polymers also, you have to understand the structure and then we need to go. That is also possible. You can use any software. Any FEA software you can use.
Okay, sir. Thank you, sir. Thank you.
Okay. Any other questions?
Any other, please?
There is no doubt, then we can close the meeting, I guess. Professor Sl.G, thank you.
Okay. Thanks, Mr. Jagadesh.
Okay.
We would like to thank you for spending precious time with us during the weekend. Help the student to know about the composite material, additive manufacturing, fused deposition modeling, like that. Also, thanks to our management and principal sir, vice principal sir, our head of the department, and my dear faculty members and our students. Thank you, Dr. Jagadesh, for a. Thank you, Jagadish.
Okay, sir. Bye, sir. Bye. Thank you.
Bye. Thank you all.
Thank you, sir. Thank you.
Thank you all.
Thank you all. Thank you.
Thank you, sir.
ப்ரொஃபசர் ராமு.
சிவலியம் சார்.
ராமு ராம்குமார். ராம்குமார்,
நல்ல பிரசன்டேஷன், நல்ல ஒரு கிளியரான ஐடியா கிடைச்சது.
நல்ல பிரசன்டேஷன், நிறைய கேட்கலான்னு பார்த்தேன், அவன் டைம் ஆயிடுச்சு அவனுக்கு.
நல்ல ஒரு அந்த இதெல்லாம். ஆனா இப்போ ஒரு சொல்ல தெரியுது, அந்த இதை வந்து நம்ம கோடு மேட்லாப் கோட்லயே நம்ம வந்து அந்த
ஆமா ஆமா ஆமா
ஆனா அந்த கோடு வந்து